Hi everyone, welcome back to the channel. In the video today, I'm going to be looking at volume as an application of integration. So what we're going to be doing is we're going to be taking advantage of the way integration works in order to find the volume of a function or a structure or two functions together. So let's see what I mean when I say that. So let's draw a graph like this, for example. Where that's y and that's x. Right? And I'm going to take, say, a straight line like that. Right? That's supposed to be straight. So we know that integration is going to find the area underneath whatever this function is. So I'm going to call that function f of x. So if we were to say take a point, say where x is 1 and x is 5, oops, and x is 5, and we integrate across here, we would find the area underneath that graph. And what we're doing when we're integrating, we're essentially taking little pieces of area and we're adding them up like this. Right? If you go to integration from first principles, then this is what you're doing. And then you add these pieces of area underneath. So you add the areas of these rectangles underneath. They're called Riemann sums. Right? And so on and so on. Now, when we do volume, what we're going to be doing is we are going to take this and we're going to rotate it around the x-axis. So when I mean rotate, we're going to have a function that looks like this, right? We're going to assume that this is symmetric. My drawing is not that great, but we're going to assume that this is symmetric. So when we rotate this, each of these little rectangles are going to become discs. So this one will become a disc like that. And like that. So you'll see this over here would be one disc. So let me just color in that disc over there. Right? And this is going to help us find volume, because you remember for any symmetrical shape, the volume is going to be the area of the base times your height. And the area of this base is going to be 1 for a circle. Now, sometimes it's very difficult to actually see in your mind's eye what this is. It's difficult to understand when you're rotating something. So let's look at a practical example of this, just to give you an idea of what I'm talking about. So let's take this glass, for example. You see this glass over here. Right, just a normal glass, an old one, because you can see there's a crack in here and everything, right? So very old glass. And if you look at the shape of this, you'll see that he's obviously symmetrical, right? He's obviously symmetrical. And what I'm going to do is I'm going to turn the glass like this. So if you look at the profile of this, you'll see you've got a straight line on top and you've got straight line at the bottom. Now, because it's symmetrical, I can look at half of the glass. So if I was to take this glass and put it onto an axis, see, so here I've got an axis, right? Here's my axis, and I put the glass on here, like that. So I'm looking at the profile. So the top of that glass is a straight line, right, which I've already drawn in. Okay, so if you look at the graph that I've got here, that is very similar to the example that I've got here. Right, so the example that I've got here for the glass, it would be this top line over here, right? So you can remember that. And if we go back to the way the glass looks, like that, right? What we're going to be doing with the integration is we're going to take discs out here, right? So that means I'm going to take the glass like this, and then I'm going to section off the glass essentially. And if I section off the glass and I turn it this way, what have I got? Circle, right? So you're going to be taking sections of the glass essentially and finding the area, or you finding the volume of that section, right? And the volume is going to be the base of that circle, the area of the base of the circle times your height, right? So that's what we're going to be doing. So if I now write this out, I'm saying I'm going to look at one disk, right? So for one disk, I'm going to be looking at volume is equal to the area of the base times the height of that disk, right? So now we need to figure out what is the base and what is the height. So if you look at your picture, your height is going to be this piece here, right? That's going to be the height of that disk over there, yeah? The area of your base is just pi r squared, right? And we've gotten this around the disk is symmetric, right? So your radius is going to be between that piece to that piece. So it's going to be pi r squared times the height here, which is essentially the change in your x value, right? Because it's going to be this value here. So I'm going to write it out and say change in x. And that is going to be v. So now we need to write it a bit more mathematically than this. We can't just say r because we need to know where that r is going to come from. Okay, so let's look at where the r comes from. So I'm going to say v, right, let's keep v is equal to pi. So where are we going to find r? Let's just remind ourselves what r is in this diagram. So if I go back to the glass, right, we remember, just remind ourselves that the glass is this, right? Then if I turn it like that, you'll see you have that circle on the base, right? So if you take a cross section of the glass, at any point you're going to have a circle. So the radius is going to be from the center of that circle all the way to the top line, okay? So that means that this here is going to be your radius, right? And so how do you find what that value of the radius is? Because remember, you're talking about the vertical height, right? So that means also that what you're looking for is you are looking for the corresponding y value here, yeah? So if you take the point on this function and you find your corresponding y value, you will then know what the radius is going to be. So if we go back to our graph here, it means that the radius is going to be, of each of the disks, is going to be this piece here, right? That over there is going to be r. And the way you would find it is to take whatever x values here and substitute into your y value here, right? That means that your r is just going to be y. So if I put r is going to be y, and in this case it's going to be squared, okay, times a change in x, and I'm going to use this notation here, right? And I'm going to use this notation here, and this means you're looking at small increments in the volume, because what you want to do here in the graph is to have these little slivers or these disks as thin as possible, because you don't want to leave out any potential volume. So for example, you don't want to leave out this piece here. So the only way you can avoid that is to make these slivers as thin as possible. And the way we write that out is to say this notation. And you remember this notation from small increments. So essentially you're saying you're taking many slices, many discs, and you're finding the volume of each of them, and then you're adding everything up. So mathematically, the way you would write that is to say that the total volume is going to be adding all of these little disks, right? So you're going to add, and add means this is the same as add. Pi y squared x. So you're adding up all your individual disks in order to get your total volume. Now, this is based on a Riemann sum. So as I said before, when you first derive integrals, you would have looked at adding up these little rectangular pieces as a sum. And those are Riemann sums, and this is similar. So then you had a scientist, mathematician, taking this formula and converting it into an integral as we know. So we then can take that and say that that is the same as the integral over some interval of pi y squared dx. And this is the formula that we use for volume, finding the integral of essentially the base times the height of those individual disks. You have to have an interval. It has to be over A and B, because a volume has a definite size, right? It's not infinite. And this, we remind ourselves, is a definite integral, right? So that is a definite integral. And when you evaluate this, and evaluate means you find the integral, then you substitute in the upper limit minus the lower limit. You end up with a number. The number is going to be squared because you're working with a volume. So if we look at an example, and I'm going to do a simple example. Say we have a function parabola. Right, we're looking at the parabola like that. And we're looking between 0 and 2, right? And our function y is equal to x squared, like that. And we want to find this piece here, the volume that that is going to create. So if we were to rotate this, we want to find what that volume is. So the volume is going to be the integral between 0 and 2, of pi y squared dx. And y in this case is going to be x squared. So it's x squared dx. So then we can simplify the integral, and we're going to have pi x to the 4 dx. The integral of that is going to be pi times x to the 5 pi, and that is going to be, your limits are 0 and 2. And when we substitute in, we're going to get pi. The function at our upper limit is going to be 2 to the 5 over 5 minus 0 to the 5 over 5. So we end up with 32 over 5 pi, and it's going to be units squared. And that is equal to about 20,106 units squared. And that's basically it. So the way it would become more complicated is if you've got two functions and you're looking at the intersection between the two functions, the difference between two functions. But an example like that, I think we should rather keep for another video. So I will see you next time. If there are any comments on this video, please leave them below. Any suggestions on what I should do in the future. If there are any parts of the video you didn't understand, please just put it in the comments below. Thank you. I'll see you next time. Bye.